light ray AO incident at O, then it takes the path OA dash with an angle theta 2. Here light is going from denser to rarer because we mentioned N1 is greater than N2. Hence light ray bends away from the normal because when it travels from denser to rarer, in rarer medium the velocity will be more, hence the refractive index will be less. Hence because of the increased the velocity, light bends more, hence it goes away from the normal. Okay, so this is what the case of refraction. The second case you can see that CO. So CO is the light ray which makes an angle theta 1 which is greater than theta c. We'll see what is theta c later. So CO is the incident light and OC dash is the reflected light. Here angle of incidence will be equal to angle of reflection. Okay, so that is called reflection. Now when light travels from denser to rarer, since the light ray bends away from the normal, there comes a situation like BO. When a light passes through B to O, then what happens? Here is the angle theta c. That means for a particular angle of incidence theta c, the refracted light OB dash, it just grazes the two surface. That means OB dash will not enter the second medium nor it reflect back to the first medium. It just grazes the surface. That means it makes an angle of 90 degree. The angle of refraction becomes 90 degree here. Okay, with the normal, the angle of refraction, that is theta 2, becomes 90 degree for a particular case called the critical angle. Theta c is the critical angle. Okay, so this you should consider to explain total internal reflection. Okay, so here we will apply Snell's law. So from Snell's law you know that the ratios of refractive indices is equal to the ratios of sine of an angle incidence of sine of an angle of incidence to the sine of angle of refraction. Okay, here what we do, instead of writing that equation, if you write like this, it is very easy. That is refractive index of the first medium, that is N1, multiply it with the sine of an angle of incidence in that medium, that is theta 1. So sine of an angle of incidence in the first medium is theta 1, right? So multiply N1 with sine of theta 1. It should be equal to the refractive index of the second medium, that is N2, into sine of the angle of refraction, that is theta 2, right? So you get this equation N1 sine theta 1 equal to N2 sine theta 2 from Snell's law. Now what happens for a total internal reflection? This theta 1 becomes theta c, that is critical angle, and sine theta 2, here theta 2 becomes 90 degree because OB dash is the light ray which makes an angle of 90 degree with the normal drawn. Hence theta 1 becomes theta c, so N1 sine theta 1 becomes N1 sine theta c, and theta 2 becomes 90. So if you substitute 90 degree here, then sine of 90 is 1. Therefore this right side of this equation becomes simply N2. Now if you rearrange this equation, sine theta c equal to N2 by N1, or theta c is equal to sine inverse of N2 by N1. This is the expression for critical angle when light goes from denser to rarer. Now you can discuss about the conditions for total internal reflection. So total internal reflection means light should not enter to the second medium. That means any angle of incidence, if it is greater than theta c, like CO, then all these light rays, they reflect back completely to the first medium, like OC dash. Okay, so that means for total internal reflection, first condition is light must travel from denser to rarer, because here N1 is greater than N2. That means this first medium, here what we considered is the denser medium and second medium is the rarer medium. Therefore light must travel from denser to rarer, and second condition is the angle of incidence theta c or theta 1 must be greater than the critical angle, that is theta c. If it is equal, then just grazes. But for total internal reflection, this theta 1 should be greater than theta c. Okay, so the theta 1 should be greater than theta c is the second condition for total internal reflection. Now we will go to the region. How it is? See, if the angle of incidence is less here, if it is less, then the angle of reflection will be less, then angle of critical angle will, the angle of incidence will be more than the critical angle, then total internal reflection. If this angle of incidence is greater than theta naught, then if it is increasing, this also increases, then angle of incidence at point B will be less than the critical angle. If it is less than the critical angle, then normal refraction takes place. That means PC light ray enters to the cladding, which is a loss. Hence, any of the light ray which incidents within this cone, that is acceptance cone, then it undergoes total internal reflection. Any of the light ray which is beyond this angle of cone, that is more than theta naught, the angle of incidence, if it is more than theta naught, then what happens? There will be a light entry to the cladding, which is a loss. So this is what the condition for total internal reflection through the optical fiber. Hence, launching of light through the fiber is very, very important. So that is what it is discussed here. Next, one more important thing, like if you take a glass rod, a simple glass rod what you use in chemistry lab, that glass rod is also a cylindrical form of a cylindrical form. Length is very large and it is circular in fashion, and surrounding medium to this glass is air medium. When you hold it in the lab, it is air medium. Then why can't you send a light ray through the glass rod, and for a particular angle of incidence, why can't you think of total internal reflection? If you try this, you will fail, because there is one more term in this for the total internal reflection which is important, for the successive total internal reflection which is important, that is fractional index change. So that is what the fractional index change delta, we generally represent it the notation delta, which is the difference in the core to cladding refractive index to the refractive index of core. Okay, this ratio, when it is very, very small, then only the chances of successive TIR is possible, otherwise not possible. Hence, when you take a glass rod and surrounding medium air, glass rod refractive index, if you consider it as 1.5 and surrounding medium refractive index as 1, then the difference is 0.5. So which is very large. That means the fractional index change is very large in this case. Hence, it is not possible to see total internal reflection successively throughout the glass rod. Hence, the fractional index change is also important for considering total internal reflection through the fiber. So just derivation is not required, just remember this expression. This is the definition of fractional index change, and its equation is delta equal to n1 minus n2 by n1. And one more small thing is there, that is relation between numerical aperture and the fractional index change. So you take fractional index change expression, that is delta equal to n1 minus n2 by n1. In this one you rearrange it, then n1 minus n2 equal to delta into n1. Don't take delta into n1 as change in n1. It is a product of fractional index change and the refractive index of core, right? Now what you do, substitute the value of n1 minus n2 into the numerical aperture expression. So what is the expression of numerical aperture? Numerical aperture is under root n1 square minus n2 square, right? It is inside the square root you have a square minus b square form. Hence you can expand it as a plus b into a minus b. So numerical aperture NA equal to under root n1 square minus n2 square changes to under root n1 plus n2 into n1 minus n2. Now in this case what you do, n1 minus n2 you substitute it as delta n1, where delta is the fractional index and n1 is the core refractive index. And then, as I said, the difference in the core and cladding refractive indices must be very, very small. Hence, by assuming that n1 is approximately equal to n2, you can replace n2 with n1, then n1 plus n1, it becomes 2n1. Okay, so 2n1 delta, and one more n1 is there in the square root, so n1 into n1, it becomes 2n1 square into delta. Okay, so you get an expression for numerical aperture after removing this square for n1. So n1 you can take it outside the square root, then you get numerical aperture equal to n1 into under root 2 delta, where delta is fractional index, n1 is core refractive index. This equation, you remember, it helps you in solving some of the numericals. Okay, while solving the numericals, that is, problems in this topic are important. While solving the problems, these equations will help. That is, the expression for numerical aperture and the conditions for numerical aperture, acceptance angle expression, and then the fractional index change expression, and the relation which connects the numerical aperture with the fractional index. Okay, so these are the simple equations you must remember to solve the numericals. So here what is happening? Increase in the value of delta increases the numerical order, right? Hence, it enhances the gathering capacity of the fiber. So delta value cannot be increased very much because it leads to some other losses, that is intermodal dispersion losses. But dispersion losses we are not going to discuss in these classes, because what the syllabus which is kept to you is the simple syllabus. Okay, so in this we are not dealing anything related to wave propagation through the fiber. But strictly speaking, to know more details about the optical fibers, knowing the wave concept is important. But here, since we are not discussing anything related to the wave propagation, only the ray concept, based on that, with lot of approximations, we just discuss the very much basic fundamental concept of light propagation through the optical fibers. Okay, so we will solve some of the numericals. I will dictate the numericals, you solve and then post the answers to me. Okay, so with this we will come to end of this class today. We will discuss more about these things and some more numericals, and then the next topic, that is losses in the optical fibers, types of optical fibers, and applications of optical fibers. In the subsequent classes we will discuss all those things. Okay, thank you very much.